Stars support themselves against the collapse of gravity through the process of nuclear fusion, slowly converting hydrogen into helium in their cores and releasing energy. When the hydrogen runs out, they start burning heavier elements, creating an enormous amount of radiation pressure, which causes the star to expand into a red giant. Soon, even the heaviest elements have been used as fuel. Without them, the star can no longer support itself, and it collapses. The outer layers bounce off the extremely dense core of the star, resulting in the biggest light show in the universe, a supernova explosion. This blast leaves behind two things: a beautiful supernova remnant, and the previously mentioned dense star core, collapsed and compressed into what is known as a neutron star. A neutron star is extremely dense. Most are only around 20 kilometers in diameter, but weigh more than our own sun. Neutron stars are also known for the radio emissions they beam from their north and south magnetic poles. When these beams cross our line of sight, we can use them to detect the neutron stars as pulsars. In this video, we're going to show you what happens when neutron stars, or pulsars, are formed from the two stars of a binary star system. More than half of the stars in our galaxy are in binary systems with other stars.
So, for example, let's say the neutron star we showed you earlier had a companion orbiting star, and that the orbit survived the supernova explosion that formed our neutron star.
Eventually, the companion star will evolve and go through the exact same process, one day becoming a pulsar itself.
When this companion star becomes a red giant, though, material from this star can accrete onto the pulsar, causing the pulsar to spin more rapidly.
The pulsar starts making full rotations in milliseconds. If the red giant star is massive enough, it will then also go through a supernova explosion. If the orbit is lucky enough to survive the blast, we are left with the rare double neutron star system. Only 1% of all binary star systems will ever make it to this stage. We've discovered about 20 of these double neutron star systems, but in only one of these systems have we been able to detect both stars' radio emission beams as pulsars. This system is known as the double pulsar system. It consists of one rapidly rotating neutron star, Pulsar A, which has a rotation period of 22 milliseconds, and one more slowly rotating neutron star, Pulsar B, with a rotation period of 2.7 seconds. The energy from the rapidly rotating Pulsar A is so strong that it deforms the magnetosphere of Pulsar B, which is shown by this green shaded region. This also affects the detectability of Pulsar B's beams through the orbit, so we can only see its beams at particular orbital phases. In this plot, we see pulse phase, or where we are in the rotation of the neutron star, along this axis, and orbital phase, or where we are in the orbit between the two pulsars, along this axis. This line shows when Pulsar A is directly behind Pulsar B from our viewpoint. The three rows of the plot correspond to the three different radio frequencies we took this data from. You can see that the pulse is only detectable at specific regions, here and here.
These correspond to bright phases of about 10% of the entire orbit.
Pulsar A also perturbs the emission of Pulsar B with a strange drifting phenomenon. This plot shows the radio pulses that are detected from Pulsar B. We see these diagonal lines, which are very unusual. If we measure the distance between these lines, though, we find that that distance equals 22 milliseconds, which you may remember is the rotation period of Pulsar A. This means that Pulsar A is directly producing these drifting features in Pulsar B's emission.
We can model this phenomenon to determine in which direction Pulsar A rotates. We found that Pulsar A rotates prograde in its orbit. That means its spin and angular momentum vectors point roughly in the same direction, just like the Earth around the Sun. This rotation has also been measured independently through timing.
The double pulsar system is the best test ever of Einstein's theory of general relativity. The pulsars in this system are getting closer over time because they are losing energy due to invisible gravitational waves, ripples in spacetime that are a key prediction of Einstein's theory of general relativity.
This plot shows the predicted shift in periastron time with date, and that predicted by general relativity. They line up perfectly. The system provides the most precise test ever of this theory in the so-called strong field regime.
The amount by which these two pulsars are getting closer is exactly 7 millimeters per day, which exactly matches Einstein's prediction. We can also use measurements of this system to measure the masses of the neutron stars in the system. We are able to do this through the measurement of relativistic effects on the orbit of the two neutron stars, all of which depend on the neutron stars' masses. The masses predicted by these effects intersect at one particular point on this diagram. The fact that all of these mass constraints agree is also very convincing proof that general relativity is the correct theory of gravity. These are the most precise measurements of stellar masses, well, aside from our own sun, ever. The plot twist in this story is that this system is no longer a double pulsar system, meaning we can only detect one of the neutron star's emission beams. Pulsar B's beam has precessed out of our line of sight due to relativistic effects. This plot shows the change in the pulse profile of Pulsar B with time.
It started off with a single bright peak, then transitioned to a faint two-peak structure, and then became very faint before disappearing completely.
Astronomers are constantly monitoring the system, waiting for Pulsar B's emissions to reappear, but no luck so far. Our best model predicts they should reappear by 2024. So, what's the future of this system? As we mentioned earlier, the pulsars in this system are getting closer and closer to each other every day. In fact, 85 million years from now, they will coalesce in what's called a kilonova explosion, releasing a huge amount of energy in gravitational waves and forming a black hole. 2 such coalescences have already been detected by LIGO, and many others should be detected over the next decade. Future radio surveys with large telescopes will also reveal many more double pulsar systems, and perhaps some with even more extreme properties.